Are you ready to delve into the world of neural networks? This video explores the intricate process of building and training these powerful models. Discover the architectures and techniques that drive modern artificial intelligence. Neural networks come in various forms, each suited for specific tasks. Fully connected layers are versatile, while transformers excel in natural language processing. Convolutional layers capture spatial data, and graph networks extend these capabilities. Other architectures like ResNet and UNet offer unique advantages. Comparing these architectures reveals differences in computational power and complexity. To build a neural network, start by choosing a library like PyTorch or TensorFlow. Programming a simple architecture involves defining layers and connections. Training requires datasets like MNIST or ImageNet. Compare train and test performance to assess the network. Adjusting layers and learning rates can improve outcomes. Before coding, grasp the basics of neurons and layers. Differentiate between feed-forward, recurrent, and convolutional networks. Learn about loss functions and optimizers like SGD and ATOM. Backpropagation updates weights based on loss gradients. This foundational knowledge is crucial for successful implementation. Data is the backbone of neural networks. Collect structured or unstructured data from various sources. Pre-process by normalizing features and encoding categories. Split data into training, validation, and test sets for effective learning. Proper data handling ensures robust model performance. Designing involves defining input, hidden, and output layers. Input layers match dataset features, while hidden layers vary in depth. Activation functions like ReLU and sigmoid add nonlinearity. Output layers depend on the task, such as softmax for classification. Example frameworks include PyTorch for implementation. Training starts with defining a loss function and optimizer. Common choices include cross-entropy for classification. Optimizers like ATOM adapt learning rates for efficiency. Training involves iteratively adjusting parameters to minimize loss. This process is key to developing effective neural networks. Evaluation uses metrics like accuracy and precision. Cross-validation and early stopping prevent overfitting. Hyperparameters like learning rate and batch size are tuned. Regularization techniques like dropout enhance model robustness. Continuous evaluation guides improvements in network performance. Once trained, models can be exported using formats like ONNX. Deploy via REST APIs using tools like Flask or FastAPI. This makes models accessible for real-time applications. Deployment bridges the gap from development to practical use. Efficient deployment ensures models serve their intended purpose. Dense layers connect every neuron to the previous layer. Used in multi-layer perceptrons for classification tasks, they also handle regression problems effectively, often serve as final layers in CNNs or RNNs. Dense layers are fundamental to neural network architecture. Convolutional layers apply filters to capture spatial patterns, essential for image processing and object recognition, used in video analysis for activity recognition. One-dimensional convolutions handle time series data. These layers are pivotal in modern AI applications. Recurrent layers are designed for sequential data. They maintain memory to capture temporal dependencies. LSTM and GRU handle long-term dependencies effectively. Used in NLP, time series prediction, and speech recognition. Recurrent layers are crucial for processing sequences. Transformers use self-attention for parallelization and scalability, ideal for NLP tasks like text classification and translation. Vision transformers apply these concepts to image tasks. They support multimodal models combining text and image inputs. Transformer layers revolutionize model efficiency. Normalization layers stabilize learning by normalizing inputs. Batch normalization speeds up training and improves stability. Layer normalization is used in transformers for feature normalization. These layers reduce internal covariate shift. They are essential for efficient deep learning models. Dropout layers randomly set input units to 0 during training. This prevents overfitting by adding regularization, common in fully connected and convolutional layers. Dropout enhances model robustness and generalization. It's a key technique in neural network training. Pooling layers downsample input by reducing spatial dimensions. Max pooling selects maximum values, while average pooling computes averages, used in CNNs to make features invariant to shifts. Pooling layers are vital for efficient spatial data processing. They simplify data while retaining essential features. Embedding layers convert categorical data into dense vectors. Widely used in NLP for word embeddings like Word2Vec. They enhance recommendation systems with item embeddings. Embedding layers capture semantic meanings in data. They are foundational for text processing tasks. Attention layers focus on relevant parts of input sequences. They are crucial in sequence-to-sequence models, used in transformer architectures for dynamic focus. Enhance tasks like image captioning and machine translation. Attention layers improve model interpretability. Residual layers add input to output for shortcut paths, used in ResNet architecture for image classification. They combat vanishing gradients in deep networks. Residual layers enhance model depth without degradation. They are vital for building advanced neural networks. Training strategies involve optimizer choice and learning rate management. Gradient descent is the core approach for parameter updates. Regularization techniques prevent overfitting during training. Early stopping monitors validation loss to halt training. Effective strategies ensure robust model performance. Evaluating performance involves comparing training and test data results. The training test gap indicates generalization capabilities. Metrics like accuracy and loss guide performance assessment. Techniques like cross-validation enhance evaluation robustness. Effective evaluation ensures models meet their intended goals. In conclusion, building and training neural networks requires a clear and structured approach. From understanding architectures to deploying models, every step plays a vital role. By mastering these techniques, you can truly harness the full potential of AI. Thank you for watching.